last lecture we completed longitudinal case. We were trying to see how to assess dynamic stability of an airplane for longitudinal case. And today we will make a beginning for lateral directional case. Directional case. Before we go to lateral directional case, let me give some passing remark on longitudinal case. Please understand that for longitudinal case, we have assumed small angle and also the perturbations are small, and that helped us in decoupling longitudinal from lateral and directional case, right? But for high performance aircraft, things are a little more complicated. Okay? For example, for longitudinal case, when I model pitching moment, I write it like this: half rho v square s c bar, say cm naught plus cm alpha into alpha plus cm q into qc by 2 u1 plus cm alpha dot into alpha dot c by 2 u1 plus cm delta E into delta E. But you will find if the angle of attack is much higher and which violates our small angle approximation, then there are additional term that has to be incorporated. Also, if the rates are very fast, again we have to incorporate it. Lots of terms which are predominant by unsteady effect. Okay? Just to give one example before I conclude, if I take a cylinder and if I go on increasing the angle of attack, the flow is coming like this, what you will see is there will be generation of vortices, because as air is coming like this, there is one component in this direction and they flow and they will create a asymmetric vortices. One could be like this, one could be like this, and this will create a side force and which will again create a yawing moment. So, this yawing moment for high angle of attack, this yawing moment is actually coming because of angle of attack, which is pretty high, right? So, in yawing moment, when you will be modeling yawing moment, we have to see that for high performance aircraft, the yawing moment will become function of angle of attack. Similarly, if you take beta, that is, this is the body and wind is coming from here, side wind, and let's say this is beta. If this beta is large, then because of beta, there will be pitching moment. And in such cases, we have to add additional term, I say half rho v square s c bar into cm due to beta, right? So, there is a coupling now. You could see there is a coupling between directional and longitudinal cases. Similarly, there will be terms which are dependent on the rates, on the history of how the flow has built up, okay, because of high oscillations. So, whole of this aerodynamic model become highly nonlinear. However, so far whatever we have developed, we have assumed things are linear, right. So, that becomes a challenge for analyzing dynamic stability by using this method. Yes, if you can linearize this judiciously, then this can be easily applied. Okay? But this is an area which we need to understand and keep back of your mind. So, we come back to lateral directional case. Before we start going into dynamic stability, we will revise few things. If this is my airplane, and how do we define beta? Beta was, this is the airplane, I would say the top view. I am flying in this direction, and if relative wind is coming from my right, if I am the pilot sitting here, then this is positive beta. Okay. And what was the condition for directional stability? Directional static stability. The condition was, if I plot Cn versus beta, then Cn beta should be greater than 0. That is, Cn beta greater than 0. So, how do I understand that? If there is a beta, the vertical tail will generate a force in this direction, which will give moment about Cg. Which moment? This is yawing moment. And what is the sign convention for yawing moment? We know that if I am flying like this, right wing going back is yawing moment positive, and right wing going down is roll moment positive. In this case, we are talking about a yawing moment. So, for a positive beta, if you want to counter this beta, if it has to have a tendency to make beta 0, then it has to turn towards right or generate a positive yawing moment, and that is how Cn beta greater than 0 was the condition for directional static stability, and primary contributor was vertical fin or vertical tail. Okay. This we know. For lateral case, understanding is this: suppose I am looking from the back and this is my vertical tail, and because of some reason it has developed a bank. I am going like this, it has disturbance, bank disturbance has come. So, if it is statically stable in lateral mode, then it should automatically generate moment which will try to give a negative rolling moment, right. So, for a positive bank, negative rolling moment. So, how do you model this? What is the mechanism? Mechanism is, if the airplane is like this and there is a bank, then it will start side slipping. As it side slips, there is a vertical tail which will give a force, and that will give moment, right. That is, if this is having a bank, it will start side slipping. So, relative air will be like this. This will give a force on the vertical tail, that will give a moment about the center line, which is a negative moment or negative rolling moment, negative rolling moment. And in non-dimensional form, we said dCl by d beta less than 0. We have seen that I can have lateral stability through vertical fin or vertical tail. Also, we can have through high wing as well as by giving a dihedral. All these things we have covered earlier course. Okay. Just I thought I will revisit this. Now, we are talking about dynamic stability, we are talking about the transient. So, it is important that we understand what are the forces and moments will be primarily concerned. If this is x, this is y, this is z. One will be side force, that is along y direction. Second will be rolling moment. That is about x axis, and third will be yawing moment about z axis. And we know the sign convention. As rolling moment is concerned, right wing going down when I am flying like this is positive, right wing going back when I am flying like this is yawing moment positive. Right. Now, the next question comes, how do I functionalize the side force, rolling moment and yawing moment in terms of control variable and motion variables, right. So, if I write y as side force, I write its function of beta, let us say roll rate, yaw rate, aileron deflection and rudder deflection. We are talking about small angle and small perturbations. Similarly, if we assume this is okay as a good approximation, rolling moment, I say L. Please don't get confused, L is also used as lift, but we are talking about rolling moment. So let me write small l, that will be, okay, so again I will have P, B, rolling moment function is function of beta, roll rate, yaw rate, aileron deflection, rudder deflection, and yawing moment N, again function of beta, P, R, delta A, delta R. You understand what is delta A? Delta A was aileron deflection, right? If this is my wing, here there is a flap, and here there is aileron. By deflecting the aileron, I can generate rolling moment. Okay? So that is why delta A. What is important also to understand that if I have a vertical tail like this, and this is the rudder, if I deflect rudder, this also can generate rolling moment, isn't it? Because if I deflect the rudder and suppose the force is coming out of the blackboard like this, or let me draw it correctly, suppose it is coming out like this, then this will also give a rolling moment about this axis. Okay? Just to make you more clear, if this is the fuselage and this is the vertical tail, okay, then if I deflect the rudder like this, right, then as it is moving forward, it will experience a force towards me in this direction, and this force into this distance will give a rolling moment. If you see like this, if I deflect it like this and moving here, force will be towards me. So this force into this distance will give me rolling moment. So rudder also will generate rolling moment in addition to yawing moment. Okay. So now let us first check whether side force will depend upon beta, roll rate, yaw rate or not. This is important before you go for transient analysis of lateral and directional case. I will take simple example. If I see this is the fuselage and this is the vertical tail, right? If there is a beta, I am looking from, if there is a beta, wind is coming from this side, relative air is coming from this side, I am moving actually towards this. Then, yes indeed, this gentleman, the vertical tail also will see beta angle, beta side slip angle. Okay. You will see that soon. As soon as I put a wing here, it will indeed see some angle beta, but it will be different than beta in terms of magnitude because of side wash. It is a similar thing as it happened for angle of attack at the horizontal tail. That was different than the angle of attack seen at the wing because of downwash created by the wing. Similarly here, instead of downwash, it will be side wash. We will discuss about those, right? But whatever beta comes, that will give a force this side, and as far as our axis system is concerned, if it is x, it is y, and it is z, then you will find there will be, for a positive beta, the force along y direction will be negative by this convention. That is, if you see this is x, towards you is y, and this is z. If there is a beta like this, the force is in this direction and y is in this direction. So, for a positive beta, the side force will have a negative sign. Okay? This is because of our axis system. Right? But there is no doubt about it. If there is a beta, vertical tail will give you side force, fuselage also will give you side force, and depending on what type of wing, they also will contribute. However, predominant will be the vertical tail, right? What about P? Will it be function of P? That is the second question. Now you see, if I rotate this body about x axis, let me demonstrate it here. We are examining whether there will be a side force because of roll rate, that is rotation about x axis, you could see if it rotates about x axis, this vertical tail will see a relative wear which is p into this distance, right. For example, if this is the vertical tail and rotating with p, so at any distance r, there will be a relative air speed, right, which is equal to p into r. And that, in addition with, it is moving with a velocity v, that will give you roughly a beta which is equal to p r by u1. I am saying with u1 it is moving forward, right. The moment there is a beta which is because of p, this beta will give a side force. So, hence there has to be a side force because of p. This part clear? As I rotate it like this, there is a PR, relative air speed, moving forward. So, there is a beta, and this will give a side force in this direction. So, it is correct to assume that because of p there will be side force. What about r? If I see like this, r is yaw rate, that is I have to rotate about z axis. I rotate like this, positive r. As I rotate like this, you could see this vertical tail will be seeing relative air speed which is equal to, if I draw it like this and I say this is Cg and this length is, let us say, Lv, then there will be relative air speed to r into Lv and divide by u1, again that will be delta beta, right. So, since there is delta beta, and you know because of this there will be a side force. About delta r, you should not have any confusion. If it is a rudder, if I deflect the rudder, for example, towards this direction, then there will be a force into the board, or if you see this, if this is the vertical tail and rudder is positively deflected towards left. Okay, please see this, straight towards left is delta r positive. As I am moving forward, there will be a force in this direction, and this is x, this is y and z. So, positive delta r will cause a side force in the positive y direction, right. So, the point is delta r also will cause a force along y. For time being, delta a will assume that it hardly contribute any force in the y direction, right, at the first approximation. Now, you could see this rolling moment and yawing moment are because of this side force y primarily. If there is a force, there will be a rolling moment, there will be a yawing moment. For example, if force, center pressure of force is acting at this point, then this force into this Lv distance will be the yawing moment contribution. This is y. So, y into Lv will be contributing towards yawing moment, and y into this distance, let us say r bar, will contribute towards rolling moment. So, once y is function of this, automatically rolling moment and yawing moment also gets function of all those motion and control variables, right. With the difference that for side force, we are telling aileron deflection will not cause much of a side force as a very first approximation. However, for rolling moment, delta A aileron deflection is very dominating. It creates the active rolling moment, right, we use as a control. Similarly, for yawing moment, delta R rudder creates the active yawing moment, and we use rudder for directional control, right. Please understand, when you in flying, we will be using all these in combination, right. Okay.